All right, systems of equations with substitution. So there's a few ways to solve a system of equations. Substitution is the one that, in my opinion, is the most intuitive. Let me show you an example, then you can try one on your own. So imagine you have two equations. You're trying to find the values for x and y that would make both equations simultaneously true. All we're going to do here is see how y is isolated. We're going to take what y equals, which is 5x minus 4, and we're just going to plug that in for the second equation. So if I rewrite the second equation, instead of writing y now, I'm going to write what y equals, which is 5x minus 4. No, sorry about that. And it equals 10. And now we just solve like a normal equation. 7x minus 4, add 4, 7x equals 14, and of course x equals 2. The extra little bit of work you have to do here is I don't want to just know what x is. I want to know what y is also. So I'm going to take this 2. I'm going to plug it back into either equation. I'm going to try the first one here. So I've got y equals 5 times not x. We know what x is 2 now, minus 4. We get minus 4. So y equals 6. And then just to make it look a little nicer, call me old fashioned, I want to write this as an ordered pair. So instead of just saying my answer is x equals 2, y equals 6, I'm going to write it as 2 comma 6. I'm going to put a little box around it, and your math teacher is happy. All right, try one on your own here. All right, pause the video, try it out, and we're back. Did you get 0 comma 2? Take a quick look. If you want to see what I wrote down here, I'll move this around. And that is an example of substitution problem. The only additional thing you had to deal with here was you had to distribute this 3 that was in front of the y. Otherwise, same stuff that you all know how to do. All right, what if we make it a little bit more interesting? Whew, x squared. Same idea here. We're going to take what y equals. Also could do this with x. Plug it in here. So this turns into 2x plus 5 equals x squared minus 3x minus 1. If you've got an x squared and an x in the same equation, easiest way to solve is to get everything on one side. So I'm going to subtract 2x, subtract 5, so you get x squared. If you minus 2x minus 2x, you minus 5x minus 5 minus 5, you're going to have minus 6. And at this point, you could do, sorry, it's not writing. At this point, you could do quadratic formula, but you all know how to factor, so I recommend that. You could do your magic diamond if you do it that way. I'm just going to figure out two factors of negative 6 that add up to negative 5, and we get that x could be 6 or x could be negative 1. Same thing, we don't just want to know what x is, we want to know what y is as well. So I'm going to take those two x's, plug them back in up here. I like the second equation, so for x equals 6, if we plug that in for this equation, I'm going to get y equals 2 times 6 plus 5. That looks like 17. So that ordered pair is going to be 6 comma 17. I also want to know when x equals negative 1. Plug it into the same one. Y equals 2 times negative 1 plus 5. Negative 2 plus 5 is 3. So y equals 3. So that ordered pair is going to be negative 1 comma 3. And our two answers are 6 comma 17, negative 1 comma 3. If you plugged 6 comma 17 into the first and the second equation, it would make it true. Same thing with negative 1 comma 3. So there were two solutions. If you were graphing this, there would be two intersection points for that parabola and that line. Let's try one on your own here. All right, so pause the video, see if you can try out this one. And we're back. Did you get these answers? Let me move me. Ooh, I'm smaller. Okay. And did you get negative 3 comma 14 and 1 comma 2? Again, those are your two solutions. You should be able to plug that into both equations for x and y, and it should make it true. All right. Last thing, we have some special cases, don't we always? So imagine if you were to solve this first one. Plug in, let's plug this in for y over here. You'd get 2x plus 7 equals 2x minus 3. Subtract 2x, subtract 2x. and my x's go away and you get 7 equals -3. That's not true. This would be no real solution. And if you were thinking about this graphically, why would that be? Well, if you were to graph 2x minus 3, it's going to look something like this. If you're going to graph 2x plus 7, same slope, different y-intercept, these would be two parallel lines. This system has no real solution because those two lines will never intersect. There is no value of x and y that would work for both equations at the same time. So no real solution. How about this one? If that one's no real solution, what's this special case going to be? Well, let's find out. If we plug this in, -6x plus 2 times 3x minus 4 equals -8. Doesn't fit. We get -6x plus 6x -8 equals -8. Uh-oh, my x's cancel out. I get -8 equals -8. So normally, this would be our ARN solution, except any real number or all real number doesn't really make sense here because I can't plug in like 1 comma 1. That doesn't make either of these equations true. Oh, it almost did. Instead, it turns out that if you were to graph these, this would actually be the same line. So I know, I mean, it's kind of dumb, but it turned out these two equations were actually the same exact thing. So instead of writing any real number, all real number, we're going to write IMS for infinitely many solutions, or lots of math teachers will like that, or I always thought APOL, which means there's more than one solution here, but any point on the line would work because this point, or this point, you can't see it, this point. There's infinite solutions, but that's different than saying any number in the universe would work. So infinitely many solutions, any point on the line, or you can just write a note, say, Mr. Spooner, these are actually the exact same line, and I'll know what you're talking about. But we can't just write any real number. So that's solving systems by substitution. Good luck.